Cool. So now, switching gears from what Thomas just covered, want to give like a very quick update on some of the new LOM code that Yehan has written. Just like a very quick sneak preview. So I'll just show like a design that we can use the new LOM code on, and then pass it off to Yehan. He'll sort of skim through some of the basics of LOM and then show how the new code works. So before I begin, just want everyone to keep in mind that this code hasn't been merged into main yet. Some parts of the code will change based on the extensive render analysis code that Marco has written. So just keep that in mind. All right, so without further ado, let me just run through these cells to show one design that the LLM code could be used on. All right, so as usual, we'll enable automatic reloading of the modules and go through the usual imports to make sure that we can create our design in Metal. And so while that's loading, okay, here we go. All right, so today what I want to show is just a system that consists of two transmons and two readouts that are attached to, well, one readout per transmon. Right? So first step, of course, is to draw the transmons. And so these transmons, right, you notice that they have two pads each, and they're connected by a single short coupler between them. Right? And now what we want to do is to add two open to ground terminations on either side of them. Right, so let me just run the cell, and then you can see where they're located. Okay, so one is at negative 1.50, one's at 2.50. And what we want to do right now is to draw readout resonators of a specific frequency. Right? And so in order to meet that frequency requirement, we need to ensure that the readout is of a certain length. And so we can go ahead and do that by using this function here, find resonator length, which uses another method within CPW calculations here. So in this example, suppose we're interested in having resonators with 8 and 7.6 gigahertz, right? So pretty close. So this is how we would do that. We just run this, and we find that, interestingly, that one of the resonators would need to be 7.6 millimeters, the other would need to be 8. Right? And so now all we have to do is use the route meander class, right, to actually draw the CPWs, right? And we feed in the total length right here, right? The options for the first CPW and the options for the second one right here, and connect them to the appropriate pins and components. All right, so on the face of it, it doesn't seem that different, but there are, again, like small differences in the lengths. If we look here at the total length, it's the number that we just passed in, right? And for the second CPW as well. All right, so now that we have the design ready, we want to render it into ANSYS. And so again, this is using the code that exists in main right now. This is going to change once the render analysis code is merged. So we want to create a new Q3D design in ANSYS. Right? And so let's wait a bit while that happens. Right? So now we see two transmon here, and we'll notice that there's already a setup that's present. Want to make sure that ANSYS draws the design the way we want it to. So here we're assigning like a fixed buffer width, right? And also there's similar wire bond options here. And you can check the options after you set them. And we'll go ahead and render just one of the transmons at a time. Okay, so that's our transmon, pretty straightforward. We can make sure that everything is as we expect, right? So again, just as a reminder, we've attached open end caps to both of these pins, which were formerly connected within metal. So both of these are open. All right, and using the setup that we already have right here, we'll go ahead and analyze it and extract the capacitance matrix. Right. So this might take maybe a minute or two. But in the meantime, are there any questions on what I've done so far? Okay, great. Then we'll just wait a couple minutes for this to finish. Oh, one other thing I'd like to add before, well, while this is running, is that these transmons are slightly different. So, oh, seems to be some lag. Yeah, so the transmons are slightly different in that the pads for Q2 are slightly wider and thicker than the pads um, for Q1. So you'll see that the capacitances will differ accordingly. Right? So there's a smaller gap between these two main pads in Q2, but otherwise the overall design is the same. Let me see if I can pull it back up. Okay, so right here. And you see that the pads in Q2 are wider. The gap is slightly smaller, but otherwise it's the same. Okay, so it seems like the setup has finished running. So let's get the capacitance matrix. And so when we run get capacitance matrix, it tells us where exactly this is saved, right? So right here, it's under C, users, dentists, etc. So I can just go to that folder and find the file, which will be saved as a text file, right? And then this capacitance matrix will then be passed on to the LOM code, which will process it further, all right? And we can do the exact same thing with the second transmon. So let's delete this first one. And we can do the same thing. We'll analyze the setup and get the capacitance matrix for it. All right. So, I mean, these two steps are basically a repeat of before, so won't go through it. But for now, we can just go to that folder and get the text file, and then we'll assume that, all right, having obtained that, we'll pass on to LOM code. So here it's represented as a pandas data frame, but right, we'll have a text file and go from there. All right, so any last questions about this design before we move on to the main LM topic? Okay, if not, I'll let Yehan take it away.
Great. I'm going to share my screen.
Right.
1 second. Great. Can folks see my screen?
Yes.
Great. Okay. Thanks to uh, to Dennis for the design. And so now I'm gonna give people a sneak peek of our new LOM analysis. As I want to emphasize that this is not supposed to be a comprehensive tutorial of the LM analysis. I want to refer folks to this tutorial that Zlatko and Dennis did a couple of months ago, and then if you want to know more details, you can also check out Zlatko's and Thomas' paper on this. And I'm pretty sure that we'll also do more tutorials on this in the future. But this today, I just want to give you kind of like a sneak peek, behind the curtain sneak peek of a new analysis feature that's coming. And so it's basically a teaser, if you will. But I'll still give you a quick, just kind of summary of LM analysis so that we can be on the same page. So the summary I want to give is basically I like to think of the way I like to think of LLM is kind of like how I like to think of the divide and conquer algorithm in programming. So what does that mean? So basically you want to partition your complicated composite system, your device, into cells, and then you simulate each of those cells individually, and then you once they're simulated individually, and then you create a composite system from these individual simulations, and then with this composite system you can then further reduce that composite system, and you can map it to known building blocks that you can treat separately. And so then so for each known building block, uh, you can model its Hamiltonian. So we call each of those building blocks a subsystem. So you can model its Hamiltonian, and you can model the pairwise interaction Hamiltonian of each of those subsystems, and then you can come up with the full Hamiltonian in such way that describes the entire system. So this is just kind of like a really quick overview. So let's do a concrete example using the design that Dennis just showed you guys. So here we have this design. So let's first partition it. So okay, so we have cell 0, which it just contains the resonator. We have cell 1, which contains a couple different systems. So it contains the qubit, the coupling pad from resonator 1, and also uh, a, a pad that's connected to the direct coupler. We have cell 2, which contains the second qubit, the coupling pad from its resonator, and also a coupling pad connected to the direct coupler. And then finally, we have the fourth cell, which just contains the resonator. So this is the 4 cells that we're going to partition our system into. All right, so now I'll show you kind of the main steps of the LM analysis. So first, as I alluded to earlier, we want to simulate the cells individually. So this is something that Dennis just showed you. So he simulated cell 1 to extract to extract the capacitance matrix, and typically that's what we get out of ANSYS. And you could also get the inductance matrix out of ANSYS that way, but typically we would set those inductances in manually. So similarly, like Dennis showed you, we also extract, we simulate cell 2 and extract its capacitance matrix, and then the next step is we want to create the composite system. So after step 1, we have these capacitance and inductance matrices. So when we want to create the composite system, and this composite node basis, essentially you just add them up. So imagine you have this. So you add your capacitance matrix from cell 1, and you add the capacitance matrix from cell 2, and in this composite basis, now you have your capacitance matrix and inductance matrix that describe the whole system. So the next step is, okay, once you're in this composite basis, you want to reduce and then map them to building blocks and their pairwise interactions. So here I want to show this kind of in a pictorial way, so to help you understand. So basically, you have this big matrix, and then through this process, you reduce the dimensionality by removing nodes that are not dynamical, and so you're in a reduced space, and then in this reduced C and L matrices, you can basically now map them to existing building blocks. So essentially, in this reduced matrices, you can identify the diagonal elements. You can map the diagonal elements on your C and L matrices to the Hamiltonians of your subsystems, and the off-diagonal elements to the interaction Hamiltonian of your between these subsystems. So, and I want to say that as a user of LM of this new LM analysis, you don't really have to worry about any of this operations I mentioned here. That's just so you understand what's going on behind the curtain. But this will be all taken care of for you by the LM analysis. So now let's so with this quick overview in mind, let's quickly. I'll give you a teaser of this new LM analysis. Let me just now bring this. Once I'm just going to share my notebook with you. If I can bring this notebook. All right. Let me stop sharing for a second and then share a different screen. That's maybe the fastest way. Okay. All right. Can folks see my notebook?
Yes.
Okay, great. Okay, so now I'll show kind of just a working example of this new LM analysis code. And as Dennis mentioned, this is not in production yet, and it will be in production soon. But this is just to give you like a kind of like a quick taste of what's coming. All right, so Dennis he showed you that we saved the capacitance matrices from those two cells. So here I'm just reload them. So these are the two capacitance matrices from the simulation. And then first I would make two, based on these two capacitance matrices, I'll construct two cells. So basically, so here I set up the options for cell 1, option for cell 2. Essentially, I just pass in the capacitance matrix, and it's and where the inductances are at this value and where the junctions are. So now I have this two. Now I have this two cells, and then I make two. I create 4 subsystems corresponding to the 4 subsystems that you saw. So 2 resonators and two qubits, 2 transmons. So here I create subsystem 1, which is a transmon, subsystem 2, another transmon, and then here I create the corresponding subsystem for the 2 resonators. So here we have resonator 1, and then connected to the first qubit, and the resonator 2 connected to the second qubit. And so with my subsystems and the cells defined, I can create the composite system. As you can see, right now I'm being very explicit with the steps. I want to kind of mirror what I showed you in that quick presentation. So of course, when we integrate this new LOM analysis with the rest of metal, the steps here can be more streamlined. But here I'm being explicit. And also, nonetheless, what I'm showing here will also be useful to users who want to use the LOM analysis code directly if they don't, if they have their own results saved somewhere without needing to setting up the renderer and or the other steps in metal. So, okay, so here we have the composite system where I just pass in the subsystems I created and the cells. And so I create this composite system. And so here is this step, circuit graph, is a intermediate step that you don't really need to. It will be done under the hood for you. But I just want to print the results. You see here is kind of what I showed early. So here, this is the node junction basis. This is the composite node basis once we can create a composite system out of the 2 cells. And this node's keep is when mentioned earlier, when we want to reduce the composite system to a reduced system. This is the nodes that have been reduced to. So these are the nodes that are kept, and then these are the reduced inverse inductance matrix and reduced capacitance matrix. Again, this is just to show you to be explicit about it, but you don't really have to worry about these matrices when you're working with this new LOM analysis. And then finally, we calculate the Hilbert space of this composite system. So then we can model the Hamiltonian of this composite system. So here I'm just running this to show you the Hilbert space, and this is power enabled by the wonderful package created by Yang and company. So here you can create Hilbert space on this composite system, and shows you the created Hilbert space with interaction as well. So with the G's, and then finally you can basically call the Hamiltonian function on the Hilbert space, and then we can print the results. And now you can see we get the system frequency, so the frequency for the qubits and for the resonators. And you can see that due to the coupling between the subsystem, remember Dennis showed you that the frequency for the key 7 to 8 gigahertz and a 7.6, and you can see this pretty close, but with the loading effects from the other systems, so they are of course changed. And then we have here the chi matrices in megahertz. So on the you can read the diagonal elements sort of as the n harmonicities of the different modes. So about 350 megahertz n harmonicity for the first qubit, about 300 for a second qubit, and then the off diagonals are the chi's. So this is the chi between the qubit 1 and readout resonator is about 5 megahertz, and the chi's between the second qubit and its readout resonator is about 1.5 megahertz. So yeah, so this is basically a quick sneak peek of this new LOM analysis.